So for our last, but certainly not least, speaker of the day, we are going to have Kevin Bateman. Kevin's a retired PK/PD and drug metabolism expert. And just as a brief overview of his presentation, so it has to do with high-resolution mass spec, which we've long sought to be a viable alternative for quantitative workflows, but has been unable to broadly compete, mainly due to the lack of suitable data processing software. So Kevin's going to talk to us a little bit about molecular structure dependent workflow, the holistic and user-independent processing of HRMS data, as well as the automatic quantitation of small drug-like molecules. So with that, Kevin, welcome. I'll turn it over to you.
Great. Thanks very much, Jamie. Pleasure to be here. Yeah, I'm going to talk a bit about the forgotten world of small molecule drug discovery and quantitation. We heard a lot about proteins, but I'm going to talk about small molecules. And I'm going to cover a couple topics. One is the high-res data processing, but the other is MRM-based quantitation, which is still the king of quantitation for small molecules, and some work that was done by BMS in collaboration with Mass Analytica that was presented earlier this year at ASMS. I was able to steal their slides. And it's really about transition prediction using a model built from their MRM database. And then I will transition to high-res data processing, really a structure-driven approach, and how an algorithm can be built for automatically selecting all the optimal features you need to build a quantitative method, whether it's the ions, extraction window, integration parameters, regression model. And that was a collaboration, again, with Mass Analytica, but with Merck, where I worked before I retired last year. So these were slides Shivani Patel presented at ASMS around that using a learning to rank model, which is a machine learning based approach, to build a predictive model for MRM. So Ramon is the person at Lead Molecular, which is a part of Mass Analytica, that built the model. And so what's the need here, right? So currently, if you're doing small molecule quantitation in an ADME type environment, you optimize your compounds using a flow injection based approach to get the Q1, Q3, collision energy, DP voltage. And this is a well-established workflow using something like Discovery Quant software if you're on a SCIEX platform. And all the major pharma have built these types of databases. So at BMS, they say they have 80K plus compounds, right? And so can you take this data, because it takes about 2 minutes per compound, you're getting new compounds all the time, to build a model instead of doing this optimization to predict what a new compound MRM transition might be, right? So the current workflow is you get a new compound, you do the optimization, and then you go do sample analysis. But can you use your existing data to use machine learning based approaches, and specifically a learning to rank based approach, to get that MRM transition without doing the optimization? So I'm not a data scientist, and I'm not going to pretend to be able to speak to this slide in great detail. I would recommend contacting the authors of the paper, specifically Ramon, about how he did this work. But basically, they took about 6,000 compounds across 90 diverse programs with up to 7 MRM transitions per compound, and then built a model using these tools. And they did their split and validation type approach, and were able to train the model, right? And so basically, if you have a high predicted intensity, you get a higher number, right? So here, verapamil, which you all know and love, predicts the fragments intensity based on the structure and that learning to rank model. So does this work? So this is data again. So this is permeability type data. You're analyzing verapamil across a series of permeability experiments. This is data using the optimized, so where you would have used a traditional MRM flow injection, get the collision energy based approach. And this is the same samples run using an MRM transition from the predicted approach, right? And so the data for verapamil turns out to be pretty close, right? And so it shows in this simple case that a learning to rank predicted MRM allows you to get acceptable data. And so what Bristol Myers did was take it into a larger data set. So they did a total of 192 compounds, n equals 3, analyzed it twice. Once using their optimized MRM, and that same set of samples was then analyzed using their predicted MRM. And so they were able to show good uniformity, close to 1, across all of these assay data points, greater than 0.85% correlation, right? And so basically, it demonstrates that you can get equivalent biological data using a predicted MRM versus using an optimized MRM. Right, so the future of MRM-based quantitation then looks like it's evolving by using these machine-based approaches to build a model from historical data, and then use that model to analyze your samples acquired using that predicted MRM, right? And so obviously the model is going to depend on the data sets that go into it, and Bristol Myers is not going to release their 80,000 MRMs and structures to the world, and so each person is going to have to build a model, or as SCIEX is doing, they'll build a model with their historical data set of MRMs, right? It's a well-established workflow, but again, it's triple quad based, and I want to talk about MRM based. But to summarize this maybe in a more modern approach, right? So if you're the analyst, you did MRM optimization, but now you're probably thinking, maybe I should be doing MRM predictors. Okay, now what I really want to talk about is high resolution data based quantitation. And here I just took a sample of papers that I found in quickly searching the literature about the future promise of bioanalysis using high resolution mass spec, right? So here's one that's from 2011, 2012, 2003. Like, it's been years that we've been saying high res mass spec is going to be used for quantitative analysis. And to some extent it does, but the reality is, will high res replace Q triple quadro quantitation? Well, we're still waiting, right? So what's the problem, right? Why do triple quads still dominate routine small molecule quantitation? Well, so there's different arguments. Could be cost, but I would argue the price of high resolution instruments have come down, and a high end triple is comparable to the price of a benchtop Q-top instrument. Complexity. Well, MS method development is less complex on high res versus MRM based. Although now if we have predictions, that argument might go away. But if you're using a simple swath based approach, there is really no method development required to do that type of analysis. Sensitivity, I would argue high res instruments are comparable to triple quads for many assays. In some cases, high res could be more sensitive than a triple quad. In some cases, a triple quad is going to be more sensitive. Really, the crux of the problem is data processing for high res. It's software. Traditionally, people who want to do quantitation with a high resolution system are dependent on triple quad workflow tools. So the software that has been built for quantitation using a triple quad is just said, okay, now use this for your high res data, and it doesn't make use of all the information that a high res system provides, right? And so here's a swath data set spectra, right? So it's a compound. This is the low energy MS, right? So you get the M plus H here. This is the MS of that window that the ion, this M plus H falls in. You get fragment ions. So if you wanted to do quantitation using high resolution, what do you use? Do you use this fragment ion? Do you use the parent ion? Do you use multiple fragment ions? What extraction window do you use? All of these questions become important if you want to get the best quality data from that data set, right? And so what ions? Do you use fragment ions, isotope peaks, addict ions? What extraction window do you use? If it's too wide, you're adding in noise. If it's too narrow, you're losing signal. And then how do you assess the quality of the quantitation? You know, which calibration calibrators do you use? How do you assess the variability based on the parameters that you're using for peak extraction, things like signal to noise, accuracy, precision? It becomes too overwhelming to do using existing data processing because you have to go back and change the settings, reprocess, see if it got better. So software is really needed to automate this process. And so a few years ago, when I was at Merck, we started a collaboration with Mass Analytica, also known Molecular Discovery, on trying to build the software that would allow us to do this automatically, right? And so we talked through what are the parameters that need to be built into an intelligent algorithm that will holistically look at all this data and come back with a method that allows you to get the best quality quantitation from high resolution data like swath, for example. So you need to think about how many points across the peak. What is your tolerance for extracting out your ions of interest? Things like retention time tolerances. How do you evaluate noise around each ion that you're extracting? The signal to noise ratio. How do you automatically adjust that extraction window? It's going to depend on the quality of the data, the intensity of the ions, right? And so all this become important in building an algorithm. And then how do we set up for understanding the variability in the assay to make sure that we're getting the parameters and the criteria that we want for acceptance of our quantitative assay. And then just things like how many concentration levels do you need? What's the maximum fold change between concentrations? How many replicates? How many concentrations could be removed? Practical things that analysts do when they're doing their regression analysis and selecting the points of their calibrators, right? So building all that into an algorithm becomes quite complex, but it allows you to holistically look at the data and get the best quality, right? And so I have a couple of screenshots of data of the software that's been built to date, right? So this is a swath processing method, SCIEX mass spectrometer. You can either do straight TOF MS or you can do MRM-HR swath based approach. There's a standard approach. If I had this drop-down menu live, there's a peptide approach, and I'll hint to that at the end. Your internal standard, but that's fine. What's really at the heart of the algorithm is all of these settings around peak quality, mass tolerance, how many ions you want to combine, how many ions you want to look for, and how many you want to combine. What variability do you want to accept at each level? How many concentration levels? And I've chopped off the bottom. There's weighting 1 over x, 1 over x squared, and then your regression line priority. Maybe you're really interested in driving to your lowest limit of quantitation. Maybe your samples are highly concentrated and you're more interested in having your calibration curve weighted to higher concentrations, or maybe you just want your maximum dynamic range. So the algorithm will adjust on the fly to pick the ions that meet the criteria based on the parameters that you're specifying. So the algorithm is not meant to eliminate the need of the analyst. It's really to accelerate what an analyst can do with high resolution data. And so let's go through some data now. So this is triple quad data from a 6500 plus MRM results. That spectra I showed you earlier had the M plus H of 351 and the fragment ion of 175. And this is just the stats table that you normally get out of SCIEX OS or Multiquant, whatever software you're using for your data processing. So compound, the actual concentration, how many were used, the mean concentration that's been calculated, and things like precision and accuracy, right? So I'm just highlighting that here because we're going to go through a series of these tables. So for this triple quad based quantitation, you get about 10 nanograms per mil to 10,000 nanograms per mil, right? At a discovery stage acceptance criteria of 25% accuracy precision. It's a compound specific MRM method, so you're going to get what you get, and that's it. That's good. That's what we do for triple quad based approach. So if you want to now do high res and just do TOF MS. So this is now on a 7600. The same type of table, but now we're not as good in terms of overall sensitivity. The variability might be a little bit higher, so 20 nanograms per mil. We don't get the same top end as we would on a triple. And the benefit is it's a generic TOF acquisition method. The downside is the overall sensitivity and range is not maybe as good as a triple quad. So we can turn our TOF into a triple quad by doing MRMHR, where we focus on a specific fragment ion. This gets us a boost in sensitivity. So we're actually down at 5 nanograms per mil. We still lose the high end. So we're similar to a triple quad, maybe a little bit better at the low end, but not as good at the high end. But again, it requires a compound-specific acquisition method, which is what we want to avoid. If we're going to do compound-specific, why not just do triple quad? And so now this is the output from the automated processing. So I showed you a couple of screen captures of how we set it up. And so what the software figured out was using the fragment ion and the sodium adduct, and combining those two gave the best overall results for the dynamic-based quantitation, right? So now we're down to 2 nanograms per mil. The triple quad was at 10. We've hit the top end as well. So the software has figured out that combining these two ions with whatever extraction window, I don't have it specified here, gives you the best overall quantitative results, right? And it's a generic sample acquisition. There was no tuning of the compound. It just threw it on, used a swath acquisition method, and the software figured out. Now, a human could probably figure this out, but it might take you weeks of time to get to the same result, because you'd have to constantly go through all the different ions, change all the extraction windows for each ion to figure out what was going to work best. So I said it's structure driven, right? And so that was a Merck compound, so I couldn't show you structure. So here's structures. And so what the software does, there's a bond disconnection algorithm that basically calculates fragment ions. And so that's why this is a different approach. You have to put in the structure. The software needs to know the structure of what you're analyzing, because it's going to take the MSMS and the MS spectra and then assign structures to all the fragment ions. It has to rationalize, is that ion really part of the molecule that I'm analyzing, right? So this avoids detection of background ions that might look like they're part of the molecule, but they're not, because they can't be rationalized in terms of the structure, right? And so there's this bond disconnect algorithm that is used to ensure that the fragment ions that you're using are truly related to the compound. And this is where it gets interesting, right? So again, those 3 compounds, this is triple quad data on a 6500 for the 3 compounds. And I ran wide curves 1 to 5,000. And for the most part, so verapamil and navazodone are 2 nanomolar to 2,000 nanomolar. The top end was a bit saturated. Buspirone, again, 2, but I could get the high end. It didn't saturate as much, right? So that's what we can do on a triple quad for these 3 compounds, right? So this, now I'm only showing you the dynamic output. So there's a lower limit of quantitation output, an upper limit of quantitation output that you get automatically as part of the processing. And so now navazodone, verapamil get down to 1 nanomolar. So if I go back 2 nanomolar, so I'm getting a little bit better in terms of overall sensitivity. I'm getting the full dynamic range now for these as well. On the triple quad, it was saturating at the top end. So I'm getting the full range of my calibration curve for these 2 molecules. Buspirone is not any better in terms of low end sensitivity. The triple quad's about the same. And so for buspirone, there's no difference between the triple quad and the 7600 swath. The big difference is, again, no method development. I took the samples, put them on, did a swath acquisition, and fed the data with the structures to the data processing software, and these are the results that come out. So what becomes interesting is how did these results come to happen? So as I said, there's 3 different curves that are calculated. One using wide dynamic range, one focused on upper limit of quantitation, and one focused on lower limit of quantitation. And so for nifazodone, these are the ions that were used for the processing. So nifazodone has a halogen, so you get a nice isotope cluster. So it's summing the 3 isotopes of the parent ion. Upper limit of quantitation, it's dropping out one of them because it would saturate too much. And for the lower limit of quantitation, it's adding in a fragment ion and the one of the isotopes of the parent structure in the MS-MS spectra. So it's probably adding in signal without saturating, right? So for verapamil, you could have just done top MS and would have been okay for the dynamic. For the upper limit, it's using a fragment ion. And again, so the idea here is to show you the diversity of what the algorithm is doing. It's going through all the different fragment ions that it finds that are related to the structure of the molecule and picking out the ones that are best, dynamically changing the extraction window for each of those fragment ions to meet your peak and data quality specifications, right? And so it's opening up the ability to do high-res data processing in a real-time based approach versus one that is fun to do, write a paper, but never gets used practically because it's not practical to process this type of data. So I mentioned peptides. So peptides as therapeutics are having a bit of a renaissance. Merck has a lot of focus on cyclic peptides, which tend not to fragment very well. And when they do fragment, they tend to shatter into lots and lots of different fragments. So this is just a full scan spectrum of a cyclic peptide. This is the doubly charged ion. So there's lots of ions here in a full scan based approach that could be used for quantitation. But again, the data processing is onerous. Which ions do you use for your method? Which ones do you sum? It becomes a real challenge, right? And so what I did is I took a set of samples that the analyst was running on triple quad, and it took a lot of effort to get a triple quad based method that gave the sensitivity that they needed because they were fragmenting. I took those same samples and put them on the 7600, just did a generic swath acquisition, and then gave that data and the structure of that cyclic peptide to the software to process. And this is the end result, right? And so this is PK data, so concentration versus time. The gray here is the triple quad, the yellow is the high-res mass spec at a higher dose and at a lower dose. Again, they overlap. And so instead of like 2.5 days of fighting with the triple quad to get a suitable method to collect this data, it took me all of 10 minutes to throw it on high-res system and get comparable results because the data processing allows you to automatically select the best ions that give you the signal to noise to meet the acceptance criteria that you're defining. So I'll sum up now. So 2 parts, right? The model-based prediction of memory transitions using a learning to rank methodology really enables a new workflow for triple quad, right? Without that traditional optimization, as long as you have a model built, right? And then fully automated high-res quantitative workflows with a generic acquisition really give us data that are comparable to triple quad. Sometimes better, sometimes not better, but in the ballpark that would be useful and don't require hours and hours of data processing to get you to your results, right? So this really is opening up the potential to enable automated data processing workflows for many of our quantitative assays using these new software tools. And I will stop there, and I'm happy to answer questions.